final section in Chapter 6 takes the 6 trig definitions and applies them to right triangles. You've seen this before in your geometry class when you learned about SOHCAHTOA. The first thing we need to do is expand our trig definitions onto diagrams where the radius is something other than 1. If we have an angle theta, we know that on a unit circle, this ordered pair is cosine theta, sine theta. If, however, we move to a diagram with a larger radius, this blue radius will be length r. This is also the hypotenuse of a right triangle. If I label the bottom of the right triangle x and the height of the right triangle y, I now have two right triangles that share this angle theta. By angle-angle similarity, the blue triangle and the green triangle are similar, so I can set up ratios that compare the sides. I know that the bottom of the blue triangle x compared to the bottom of the green triangle cosine theta will be in the same ratio as the large hypotenuse r and the small hypotenuse 1. If I solve this for cosine theta, x times 1 equals r cosine theta by cross multiplying, and then divide both sides by r, I find out that cosine theta equals x over r. Looking at the diagram, we see that cosine theta is the adjacent side over the hypotenuse. Cosine has adjacent over hypotenuse. Doing something similar with the y values, in the big triangle, y, and the small triangle, sine theta, is the same ratio as large hypotenuse over unit circle hypotenuse. Again, solving for sine theta, y times 1 equals sine theta times r, and we get sine theta equals y over r. Sine, looking at our diagram, sine is opposite over hypotenuse. Tangent is opposite over adjacent because we know that tangent is sine over cosine. One other quick rule that we need to learn about before we start doing examples: if I take a right triangle and if I label the angles beta and theta and label the sides A, B, and C, I know that the sum of the angles in a triangle has to equal 180 degrees. In other words, theta plus beta plus my right angle 90 degrees has to equal 180 degrees. Bringing the 90 to the other side, I've got theta plus beta equals 90 degrees. And I know that beta is the same thing as 90 degrees minus theta. I also know, using our right triangle trig definitions, that if I take the sine of beta and if I take the sine of the right side as well, sine of 90 minus theta, those must be equal. Looking at my figure, the sine of beta opposite over hypotenuse, I know that both of these have to equal b over c. Opposite side over hypotenuse, b over c. But looking at b over c compared to theta, I also know that b over c is the same thing as the cosine of theta. Adjacent is b, hypotenuse is c. That tells me that I can connect these two statements with what's called an identity. The sine of 90 minus theta is the cosine of theta. In a similar manner, we can prove the other identities. Cosine 90 minus theta is the same thing as the sine of theta, and I could also state these in terms of radians. Sine of pi over 2 minus theta is the same as cosine, and the cosine of pi over 2 minus theta is the same thing as the sine of theta. You've already seen this before because we know that the sine of, let's say, pi over 6, which is the y-coordinate, 1/2, is the same thing as the cosine, or the x-coordinate, of pi over 3. Pi over 6 and pi over 3 are connected by these two statements here. If I took pi over 2 and subtracted pi over 6, I'd get pi over 3. You could do a bunch of similar examples using degrees. The first example using right triangle trig could actually be done one of two different ways. The first way will be what we learned earlier. Sine squared theta plus cosine squared theta equals 1. Instead of theta, I actually have an a, so sine squared a plus cosine squared a equals 1. I was given sine a, so I can substitute that in. 4/5 squared plus cosine squared a equals 1. Solving for cosine squared a gives me 1 minus 4 squared is 16, 5 squared is 25. Cosine squared a equals 25 25ths minus 16 25ths is 9 25ths, which gives us cosine a equals plus or minus the square root of both of those, 3/5. Since I was told that a is an acute angle, that means that my angle, if drawn on a unit circle, would be in quadrant 1, so I'm going to keep only the positive version and get rid of the negative version. So I don't want the negative version. Once I know what sine and cosine are, I can find the other requested trig statement, cotangent. Cotangent A is defined as cosine A over sine A. So I'm going to say cosine A 3/5 divided by sine A, which I was given as 4/5. 3/5 times the reciprocal of 4/5, 5/4 gives me 3/4. That's the first method. Since we're learning about right triangle trig, method 2 would be to draw a right triangle. Since I have an acute angle, I'm going to make sure that angle A does not look obtuse. Put A here, a right triangle. Sine is defined as opposite over hypotenuse, so I can put opposite as 4, hypotenuse is 5, and do Pythagorean theorem to find the nearest side. 4 squared plus side squared equals 5 squared. Side squared equals 25 minus 16. Side squared equals 9. Side is plus or minus 3. Again, since I'm working with an acute angle, I'm going to keep all the sides of my triangle positive, so I'm going to get rid of the negative version. I can label my triangle now with a 3, and I can answer the cotangent definition using 1 over tangent definition. Tangent is defined as opposite over hypotenuse, opposite over adjacent. So cotangent would be adjacent over opposite, which in my diagram is 3 over 4. I was also asked to find cosine A. Cosine A is adjacent over hypotenuse, which is 3/5. So I get the same set of answers two different ways, and it really doesn't matter whether you use the old identity sine squared plus cosine squared equals 1. I'm still going to get cosine is 3/5, cotangent is 3/4, or whether you use the right triangle method, cosine is 3/5, cotangent is 3/4. Second example, cosine theta equals m, find the others in terms of m. I could do again either way using sine squared plus cosine squared equals 1, or I could use the right triangle. Since this section is about right triangles, I'm going to draw and do the right triangle method. Cosine theta is m. If I turn this into a fraction, I'm going to have m over 1. If I put my theta here, cosine is adjacent over hypotenuse, m over 1. And I would again need to do Pythagorean theorem to find the third side. A squared plus m squared equals 1 squared. I was given this as length m, the side that I don't know I'm calling a. A squared equals 1 minus m squared. A equals plus or minus the square root 1 minus m squared. Again, we're told that theta is an acute angle, so I'm going to use the positive version. Positive 1 minus m squared. I'm going to label my diagram. And now I can find all the other trig functions because of my diagram. Sine theta, opposite over hypotenuse, 1 minus m squared over 1. Cosine theta, adjacent over hypotenuse, m, that's the one I was given, tangent theta, opposite over adjacent, 1 minus m squared over m, and then the final three are just the reciprocal of the first three. Cosecant theta is the reciprocal of sine, 1 over 1 minus m squared square rooted. Secant theta is 1 over cosine, 1 over m, and cotangent theta is the reciprocal of tangent, m over square root 1 minus m squared. Sometimes books will ask you to rationalize this denominator and this denominator, and it's the same old way of rationalizing, just multiply the top and bottom by the square root term. The final example gives more specific information about what quadrant to work in. So the first thing I do is realize that if I'm working with theta between 2 pi and 3 pi over 2, I'm in quadrant 4, which gives me a positive x value and a negative y value. If tangent theta is negative h over 6, and if I'm working in quadrant 4, I'm going to have my diagram. Theta puts me in quadrant 4, but the reference angle that I need in order to make a right triangle will be inside the right triangle. So now I have a reference angle of inside the right triangle, and if tangent is defined as opposite over adjacent, my opposite side will be h, and my adjacent side will be 6. I'm going to label these using the negative sign either on the 6 or the h, but since I know that in quadrant 4 the y coordinate is negative, I'm going to keep the negative with the y part of my triangle or the h. Now to find the other definition, the other trig statements, I need to know again the hypotenuse. A squared plus b squared equals c squared. 36 plus h squared equals c squared. C is plus or minus the square root of 36 plus h squared. That does not simplify, so I'm going to leave my hypotenuse as that square root statement. I'm going to determine positive or negative based on my quadrant information and not in my diagram. Sine theta, opposite over hypotenuse, negative h over the hypotenuse. 36 plus h squared. I know that in quadrant 4 the sine should be a negative value, and so I'm going to leave it as negative h over a positive square root. Cosine theta, adjacent over hypotenuse, 6 over the square root statement, 36 plus h squared. And again, I'm going to leave this positive because I know that in quadrant 4 cosine statements are positive. Tangent theta, I was given as negative h over 6. And then the other three reciprocals. Cosecant theta, the reciprocal of this one, negative square root 36 plus h squared over h. Secant theta, 36 plus h squared over 6. And cotangent theta, negative h over 6. Double checking a couple things, I can see that the signs for sine and cosecant are negative, which they should be in quadrant 4. Cosine and secant are both positive, and tangent and cotangent, which are division of sine over cosine and cosecant over secant, are both negative. One important mistake that some people make is that if they see tangent theta equals negative h over 6, and if they know tangent is defined as sine theta over cosine theta, the mistake is that they take the numerator of their tangent statement and say that sine theta equals negative h and that cosine theta equals 6. As you can see, those don't match up with the answers that we got over here. The problem is that if you take a tangent statement, the denominator in both the numerator and the denominator of the tangent statement cancel each other out. In other words, the hypotenuse disappears. You still need to find the hypotenuse, so you cannot simply take a tangent statement and separate it into sines and cosines.